Welcome to the lecture series on numerical methods, a finite difference approach. In the last lecture, we have discussed about this solution by using different schemes for elliptic equation. In the present lecture, we will discuss about this hyperbolic equations, and these hyperbolic equations can be solved by using different techniques as we have discussed earlier. So, in this lecture, we will just discuss about this like explicit and implicit method based on this hyperbolic equations. So, especially if you will just go for a generalized hyperbolic equation. So, this hyperbolic equation can be written in the form like del square u by del x square, this equals to c square del square u by del x square. So, especially this is just written like any heat transfer problem or any like we can just consider as a mechanical problem where C, especially this depends on this physical constant there. Either it can be C can be defined as a specific heat coefficient, or it can be like any type of special constraints, depends on the physical scenario of the problem. So, if you just omit C, since it depends on the physical properties of the medium, so we can just write this equation in the form of del square u by del t square, this equals to del square u by del x square. And this domain, it can be lies like 0 to L here for t greater than 0. This boundary condition, if you will just see here, this requires at the end points x equals to 0 and x equals to L here. For example, if you will just consider like u of x t here as a physical problem, suppose represents the displacement of a point at a distance x at time t of a vibrating string tied between x equals to 0 and x equals to L. Then boundary condition at these points will be u equals to 0, that is no displacement. If you directly if you will just see here, so if you will just consider this domain like 0 to L here, and we are just considering a fixed string here. So, at the different points we have to provide this u data there itself at a fixed time, that is t equals to 0 there, and we will have these positions that should be defined correspondingly also there. So, that is why we are just defining this boundary condition at these points will be u equals to 0, since there is no displacement is occurring at the constant tied of the string at 2 points there. But if you will just see, there will be two initial conditions. So, that can be provided in the form of a Cauchy boundary condition prescribed at t equals to 0. One condition describes this position of each point of the string, that is a shape of the strings in x u plane, and other is specifying the velocity of each point in the plane at t equals to 0. Let these conditions are given by u of x0 is f of x and del u by del t, this equals to g of x at t equals to 0. So, if you will just see here time t equals to 0, u is defined as a function of x there, and if you just see here del u by del t, that is the time derivative, especially it is just considered as a functional value, since whenever time will get changed with respect to like positions. So, you will have a change that depends on the functional values of g there. So, these hyperbolic equations can be solved using finite difference methods or method of characteristics or many more methods it is available. But if you will just go for a finite difference method here, then we have to subdivide this domain, that is defined as like x equals to 0 to L there. So, for t greater than equals to 0 into like if you will just take here finite number of grids, that is suppose 0, 1, 2 up to n points here, then we can just define x0 equals to 0 here and xn equals to L there, and del t is the size of these time steps. So, we can just consider t equals to 0 at this level, in this line t equals to 0, then it will be incremented by del t, del t, del t likewise. And after like I steps, we can just get this grid position as in the form of I del x there, and the time position as the j del t there. Since especially if you will just take here del x, that is nothing but the distance here we are just considering. So, for first point we can just write this distance is del x here from origin. Second we can just write 2 delta x. So, likewise if you just move after like I points we can just get this one as I delta x there. And similarly we can just proceed for j direction, that is in the time scaling we can just calculate as j delta t there. So, assume that Dirichlet conditions are prescribed at both the ends points, that is x equals to 0 and x equals to L there. So, for this explicit method, if you just discretize this partial differential equation at the mass point I j, suppose I is the space coordinate and j is the time coordinate, then we can just write this one as a uij minus 1 minus 2 uij plus uij plus 1 by del t square plus order of del t square. This equals to ui minus 1 j minus 2 uij plus ui plus 1 j by del x square plus order of del x square. So, this is nothing but your del square u by del t square term, this is nothing but del square u by del x square term. So, both these if you just see, this just gives us a second degree approximated value, this is just giving a second degree error estimated value there. Or if you will just neglect this higher powers of del t, that is in the form of del t square and higher power of del x square, then we can just obtain this series expansion as in this form here. So, if you will just neglect this truncation error term, that is in the form of order of del t square and order of del x square here, then we can just obtain this partial differential equation in a linear form as ui j plus 1, since we want to find the next iterated value calculation or like a next step value here at j equals to 0, these values can be known from this initial conditions, then we have to proceed step 1 here to get all these unknown values. So, for this if you just use for j equals to 1, this is the first time step, and using ui 0 equals to f of xi, this as fi. Since at the 0th level, if you just see here t equals to 0, this only I has the variation. So, j remains 0 there itself. So, that is why we can just write this one as ui 0, and this last point if you just see here, that is just defined as in the form of f of x here, u of x 0. So, that is why j equals to 0 if you will just consider, and x at a different I points we can just consider as xi there. So, that is why it can be written in the form of ui xi and t at 0th level, this can be defined as f of xi. And if you will just use this one in the formula, then for j equals to 1 if you will just write, so we can just write this one as ui since j plus 1. So, that is why this will just give you j plus 1 means this is just giving you ui 2 here. So, r square, so I as I there itself, so ui minus 1, j is 1 here. So, then ui plus 1, j is 1 there. So, then 2 into 1 minus r square. So, ui j is 1 here minus, it can be written in the form of since ui 0 it is just written as fi here. So, ui 0 it is just replaced by fi there. So, if you will just go for like this can be used directly to find the values of u at the first time level, for that is for j equals to 0, since it involves a term if you will just see here ui minus 1 here from the initial condition there itself, that is in the form of del u by del t, this equals to g of x here at t equals to 0. And if you just write this central difference scheme for this formulation here, then we can just write this one as ui 1 minus ui minus 1 by 2 del t, this can be written as a g of xi here, and ui minus 1 it can be written as a ui 1 minus 2 del t into gi. So, for j equals to 0 if you will just see here, if you will just put directly here j equals to 0 suppose, then this will just give you like this point, that is as ui minus 1 there itself. So, this creates the problem for the calculation of this equation there. So, that is why we have to consider this initial condition to get this value, that is as u of I minus 1, which can be written in the form of the domain values there itself, ui 1 minus 2 del t into gi. So, for j equals to 0, the formula like 16.6 if you just see here, this can be written in the form of like ui 1, this equals to r square, ui minus 1, this is 0, plus ui plus 1 0, plus 2 into 1 minus r square, ui 0 minus ui minus 1 there. So, ui minus 1 that can be replaced by ui 1 minus 2 delta t gi there, and I is varying from 1 to n minus 1, or ui 1 it can be written in the form of r square by 2 ui minus 1 0 plus ui plus 1 0 plus 1 minus r square ui 0 plus delta t gi I equals to 1 to n minus 1. So, you can just check these values here. So, all values if you just see, this is 0, this is 0, this is 0. So, gi is a known value here. So, only unknown value is ui 1 here. So, that is why it can be taken to the left hand side and it can be separated. So, that is why this 2 value is just getting it off there, and we are just obtaining this all these known values on the right hand side here. So, if you just go for this molecule here, so we can just find this one as, since in the x direction we will have 3 coefficients, that is in the form of like del square u by del x square, and if you just go for time direction here, we will have 3 terms, del square by del t square here. So, this will just give you 3 terms, this will just give you 3 terms here. So, that is why this molecules, if it is just formulated, so it can be just taken in the form, if you will just see here, that is j plus 1 level, jth level and j minus 1 level. So, this coefficient is taking r square here, 2 into 1 minus r square, this is as r square here, this is as a minus 1 here, this is 2 into 1 minus r square, this is as a 1 coefficient there. So, if you just see, this is nothing but your uij coefficient, I minus 1 j, this is I plus 1 j, this is nothing but ui j minus 1, ui j plus 1. So, that is why this is the molecule, this can be formed from this equation here. And if you just go for discretization in terms of like implicit method here at the mesh point ij, such that the time derivative is replaced by the central difference and space derivative by average of central difference approximations. Since already we have considered this one in the Crank-Nicholson method, that we are just taking the average of this time scales for this like space derivatives there. So, that is why the same treatment we will just make for these equations here also. So, that is why if you just take this time difference as the central difference approximation, that is nothing but del square u by del t square, as in the form of ui j minus 1 minus 2 ui j plus ui j plus 1 by del t square plus order of del t square here. This equals to, if you will just take the average at 2 different points, at I j plus 1 point and I j minus 1 point there, we can just write this u terms as in the form of I j plus 1 point. If you will just take the central difference, then we can just write I minus 1, I and I plus 1, and j plus 1 remains fixed. Similarly, if you will just go for I j minus 1, j minus 1 remain fixed. So, I will be derived from I minus 1, I and I plus 1 plus order of a del x square term here plus order of a del t square term there. We can just define this value r as in the form of del t by del x, and if you will just neglect the higher powers of del x and del t there itself, we can just obtain minus r square ui minus 1 j plus 1 plus 2 into 1 plus r square ui j plus 1 minus r square ui plus 1 j plus 1, this equals to r square u minus 1 j minus 1 minus 2 into 1 plus r square ui j minus 1 plus r square ui plus 1 j minus 1 plus 4 ui j. Especially if you will just see here, this j plus 1 coefficients, all terms we have just kept it in the left hand side, since this terms it is unknown to us, and this I minus 1 and j minus 1, j minus 1, j minus 1, all these values are at the previous time step calculated values. So, that is why we just try to keep these things in the right hand side. And if you just see this molecule here, so j plus 1 coefficient, if you just see here, this is nothing but minus r square at I minus 1 level here, and at ith level this is just taken 2 into 1 plus r square, and at I plus 1th level it is just taking minus r square. So, these coefficients, if you just see 3 coefficients, this is just taken from these values here. And if you just go for uij coefficient here, uij is nothing but it is just associated with the coefficient as 4 here. And if you just go for like j minus 1 step values, so I minus 1 takes this coefficient as r square, this will just take as a minus 2 into 1 plus r square, and this is just taking r square term here. So this forms the complete molecule for this equation. So if you will just go for a example based on this previous discussed methods. So this function, suppose u satisfies this equation, that is in the form of del square u by del t square, this equals to del square u by del x square, where x range is lying between 0 to 1, and for all t greater than 0 with boundary conditions like u equals to 0 at x equals to 0 and x equals to 1 for t greater than 0 suppose, and the initial condition is prescribed as since already we have discussed this one u of x 0, this is just defined in the form of gx there. So that is why gx can be considered as a 2x into 1 minus x, and del u by del t this equals to 0 suppose for x lying between 0 to 1 here, and t equals to 0. So this condition, your initial conditions, if you just see here, that is nothing but it is just defined as u of x 0, that is g of x, which is in the form of 2x into 1 minus x, and another initial condition that is just given as like at different positions, del u by del t this equals to 0 for t equals to 0. Both these conditions should be satisfied, and these conditions that is just given like we have to use explicit method to obtain the solution for t equals to 0 to 1.0, taking del x equals to 0.1 and del t equals to 0.1. So this means that t has like 10 steps here, and del x also this will just take 10 different node points to get the solution here, and we have to approximate this derivative by a central difference approximation. If we will just consider like del t equals to 0.1, del x equals to 0.1 here. So especially r is defined as del t by del x, so 0.1 by 0.1 this is just taking 1 there. And if you will just put r equals to 1 in the explicit formula, this explicit formula it is just written in the form u I j plus 1, this equals to r is 1 there itself. So that is why u I minus 1 j plus u I plus 1 j plus 2 into 1 minus r square u I j minus u I j minus 1. So this is the explicit formula that I has just defined. So if we will just go for the solution for j greater or equal to 0, and I is varying from 0, 1 to up to 9 here. So at I equals to 0 the values is known to us, then our computation will go from 1 to 9 points there, since at point 1 also it is known from these boundary conditions. And if you will just approximate this derivative, that is del u by del t equals to 0, where x lies between 0 to 1 here, t equals to 0 by central difference approximation for j equals to 0, we can just obtain, that is in the form of, if you will just see here, del u by del t is written as u I plus 1 u I 1 minus u I minus 1 by 2 del t equals to g x I there, and u I minus 1 this is defined as u I 1 minus 2 del t into g I there. So g I it is just considered as a 0 there, so that is why we can just write u I minus 1 this equals to u I 1 there. So it is just written u I minus 1 this equals to u I 1, since your g of x is 0 there itself. So for j equals to 0, we can just write also this equation as u I 1 this equals to u I minus 1 0 plus u I plus 1 0 minus u I, this is minus 1. So that is why u I 1 it can be taken it off there. So that is why it can be written as half of u I minus 1 0 plus u I plus 1 0, since this will just considered at this level here. So directly if you just write this equation, this can be written as u I 1 this equals to u I minus 1 0 u I plus 1 0 minus u I minus 1 here. This can be written as ui minus 1 0 plus ui plus 1 0 minus this is ui 1. So, which can be taken to the left hand side. So, 2 ui 1 this can be written as ui minus 1 0 plus ui plus 1 plus 0 here. So, that is why ui 1 can be written as a half into ui minus 1 0 plus ui plus 1 0. And if you will just see the given problem is symmetric about the point x equals to 0.5, that is u of x 0 is symmetric, and boundary conditions as well as derivative initial conditions are symmetric. Since this is 2x into 1 minus x, if you will just put here like x equals to half here. So, automatically it can be you will have the same condition as we can just get like 0 and 1, and if you just consider like 0.25, then we can just get this one at 0.75. Since at 0.5 this remains same there itself. So, that is why all symmetricity is existing. So, one half of this calculation if you just consider, that is from I equals to 1 to 5 here, then other half can be considered as the same value there itself. And if you just go for this computation, the tabulated values, it can be taken these values as like so first step if you just see here. So, this has just considered these values at t equals to 0, then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 up to 1 here, since the increment is just taken as like del t equals to 0.1. Similarly, in the x direction if you just move here, so del x can be considered as 0.1. So, that is why this is has also taken the values 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1.0. And symmetricity means this boundary condition whatever it is just described at initial level, the same it is just described at point x equals to 0 and x equals to 1 there itself. So, it is already given that u equals to 0 at x equals to 0 and x equals to 1. So, that is why we have just written u equals to 0 at all these boundaries, that is prescribed at x equals to 0 and at x equals to 1 u equals to 0 here. And for point 1 whatever the values you will just get, it will just justified at 0.9, and 0.2 whatever the value you will just get, that the same value you can just find at 0.28. 0.3 whatever the value you will just get, 0.7 you will just get this one, 0.4 whatever you will just get, you will be satisfied at 0.6. So, for the first point calculation if you will just see here, so this just takes the values as u I 1 here. So, j equals to 1, if you will just put these values from like I equals to 1 here. So, this can be considered as a 0 0 here plus u I as 1 here. So, u 2 0 here. So, if we will just consider this first value as u 0 0 plus u 2 0 by 2. So, that is nothing but 0.18 here, and similarly we can just get this 0.9 value, that is 0.18 there, and we can just proceed in the same form, that is I will be vary from like 1, 2, 3, 4, 5, 6 sorry up to 5. If you will just go, then all points we can just get these values there itself. So, based on this calculation if you will just calculate all these values, you can just get in this form that is just described here. Thank you for listening this lecture.